On the night of November 10th, a quiet line in a routine status report changed everything. Somewhere between Mars and the Sun, an object we thought we understood stopped behaving like anything in the textbooks. The alert was simple, almost boring on paper. Preliminary analysis suggests Interstellar Object 3I Atlas has lost approximately 13% of its total mass, estimated 4 billion tons of material. 4 billion tons. In basic physics, that kind of violent outgassing is not subtle. When a comet loses mass near the Sun, it screams. It sheds ice, dust, and rock into space, carving a blazing tail millions of kilometers long. The brighter the loss, the louder the trail. There is a quiet 10th law of comets that astronomers sometimes joke about. If a comet loses mass, it must show its scars. You can bend a few rules. You can surprise us with chemistry, with brightness, with rotation, but you don't get to throw away 4 billion tons of yourself and walk away without a mark. Yet that is exactly what 3I Atlas appeared to do. When the data from China's Tianwen-1 Mars orbiter arrived, astronomers expected to see the familiar shape, a glowing head, a long torn veil of dust stretching away from the Sun, a clear direction where the missing mass had gone. Instead, the images showed something else. No tail, no fan of debris, no wisps of dust dissolving into the dark, just a dim, almost perfectly spherical glow, hanging in space like a lantern inside its own mist. From Mars' orbit, Tianwen-1 had one of the best vantage points in the solar system. Its cameras were pointed not at Mars, its home for 4 years, but at a visitor from another star system, now racing past the inner planets. What they sent back was not the roaring plume of a dying comet. It was a soft, steady halo, too smooth, too calm, too clean. At nearly the same time, on the other side of the scientific world, NASA's Jet Propulsion Laboratory was running the numbers. Using weeks of tracking data, orbital analysts noticed something deeply unsettling. 3I Atlas was no longer following the path gravity alone would dictate. The object was drifting off its predicted track, just slightly, just enough that the computers could see it. This is what scientists call non-gravitational acceleration, a tiny extra push, the kind of nudge you get when gas vents from a comet's surface, acting like a natural rocket engine. JPL's calculations were clear. To produce the measured change in motion, Atlas had to expel roughly 4 billion tons of material in just a few days. In other words, something pushed it. Hard. There was only one problem. The push was real. The evidence of the push was not. No thick tail, no expanding dust cloud, no scars in the sky. Tianwen-1 didn't see them. Mars Express didn't see them. Ground-based telescopes in Spain and Italy didn't see them. The solar system had just watched an interstellar comet shed more mass than many mountains on Earth, and somehow the universe cleaned up every trace. One cometary physicist, Dr. Robert Lunsford, put it bluntly in an internal note that later leaked: "A mass loss event this large cannot be invisible, unless something is fundamentally wrong with our assumptions." It was as if a ship had crossed an ocean at full speed, and the water behind it remained perfectly flat. For NASA, for ESA, for China's CNSA, this was not just another anomaly to file away. This was a direct hit on a rule everyone thought was unbreakable. If a comet loses mass, it must show its scars. 3. Atlas had just broken the 10th law, and there was another twist hidden in the details, one that quietly rewrote the headline. The crucial images, the ones that showed Atlas as a smooth, tailless sphere, did not come from Hubble. They did not come from James Webb. They did not come from a telescope in Hawaii or Chile. They came from a Chinese spacecraft orbiting Mars. The object that stunned NASA was first revealed in decisive detail by China's Mars probe. In a sense, Tianwen-1 became the witness that everyone else had to listen to. A distant machine circling a rust-red planet turned its gaze away from its primary mission and caught an interstellar visitor in the act of breaking a law of comets. The story in the title is not exaggeration. 3I Atlas was just detected by China's Mars probe. It did something no comet is allowed to do, and the people at NASA who read those numbers sat back, stared at their screens, and felt a cold, quiet shock. Where did 4 billion tons of missing mass go? How do you accelerate without leaving exhaust? What kind of visitor walks through the solar system, tears itself apart, and leaves the sky looking untouched? To understand how we reached this moment, and why the world's space agencies are still arguing about what Atlas really is, we have to go back. Back to the moment a Mars orbiter received a new set of instructions, a single command that told it, in effect, stop looking at Mars and turn toward the ember racing through the dark. And to understand why NASA was stunned, we must go back to the moment China's Mars probe turned its eyes away from Mars. For most of its life around Mars, Tianwen-1 had a simple, proud job. It was there to watch a world. Its cameras mapped valleys and canyons. Its instruments tasted the thin Martian atmosphere. Its orbit was tuned month after month to give engineers and scientists the best possible view of the red planet. It was never built to chase a ghost from another star. But space missions age, fuel tanks empty, primary goals are met, and sometimes, near the end of a spacecraft's planned life, engineers dare to ask a dangerous question. What else can it do before we say goodbye? When 3I Atlas slipped into the inner solar system, moving faster than any large comet ever seen, China's mission planners saw an opportunity and a risk. Here was a 5.6-kilometer-wide interstellar object, roughly the size of Manhattan, darker than asphalt, colder than steel, streaking through space at 58 kilometers per second, about 129,000 miles per hour. From Mars orbit, Tianwen-1 was sitting in almost the perfect position to take its portrait. But that portrait would not be easy. Imagine standing on a dark hillside at night, holding a camera, trying to photograph a golf ball from thousands of miles away, while the ball moves faster than any jet on Earth. Now imagine doing it with a camera that was never designed for that shot. That was Tianwen-1's challenge. The probe systems had been tuned for bright, relatively slow targets: the Martian surface, polar ice, dust storms that gnawed at the edge of dawn. Now, its guidance software had to lock onto a faint, racing ember far beyond Mars itself. For weeks, engineers on the ground rewrote code and recalibrated sensors. Every correction was a gamble. Tilt the spacecraft a little too far, and Atlas would slide out of frame. Misjudge its speed, and the object would streak past the camera's field of view in the time it takes you to blink. A fraction of a degree off, and there would be nothing but black. Tianwen-1 was, in a sense, being bent off course, not in its orbit around Mars, but in its purpose. A Mars mission was becoming, briefly, an interstellar reconnaissance platform. When the imaging sequence finally began, no one knew if it would work. The cameras opened their electronic eyes. The systems tracked a point in the darkness where mathematics said Atlas should be. And then, pixel by pixel, the shape emerged. A small, bright core, wrapped in a soft, expanding glow. No dramatic jets, no ragged fan of dust. Just a faint sphere of light, floating inside its own halo. The first raw frames were sent to Earth. They were monochrome, unprocessed, the kind of imagery only specialists usually see. But even in that stark grey, something was obvious. These pictures were sharper than anything Hubble could have taken from Earth orbit, crisper than James Webb. which was pointed elsewhere, free from the blur and distortion of Earth's atmosphere. For the first time in history, humanity had captured a close, high-resolution image of an interstellar visitor in motion, not as a streak of light or a dot on a chart, but as a resolved object with structure and presence. Tianwen-1 had done more than its designers ever asked of it. It had turned a Mars mission into a cosmic telescope. One of the mission scientists, Professor Ling Hua, later described the moment in an interview. "We aimed Tianwen-1 at a cosmic ember racing through the darkness, and the ember looked back. But the triumph came with a quiet sting, because the more clearly we saw 3I Atlas, the less it behaved like a normal comet. Its halo was too smooth, too even, like fog in a windless room. The images refused to show the chaos everyone expected, the shredded jets, the torn spray of dust. In the very frames that should have solved the mystery of Atlas's missing tail. Tianwen-1 had revealed an even deeper contradiction. The comet had changed its motion, without changing its appearance. For China, the images were a technological victory. For NASA and the rest of the world, they were a scientific problem. A machine circling Mars had just delivered the best evidence yet that something about this interstellar visitor was fundamentally wrong with our models. But the images didn't just reveal the comet, they revealed the impossible. And when astronomers fed those images back into their orbital calculations, another impossibility stepped into view. The path of 3I Atlas through our solar system was not just strange, it was unnaturally precise. Next, the question would not be how the comet looked, but how it moved. And that is where the story of invisible acceleration truly begins. When Tianwen-1's images reached laboratories around the world, astronomers did what they always do. They fed the pictures back into the math. The orbit of 3I Atlas was recalculated, refined, sharpened by new coordinates. And that is when the second shock arrived. NASA's Jet Propulsion Laboratory confirmed that Atlas was no longer following the simple, elegant curve predicted by gravity alone. Its path had shifted, subtly but unmistakably. To most people, that deviation looks like nothing more than a tiny bend in a long, cold line. But to orbital physicists, it was the equivalent of seeing a fingerprint on a locked safe. Something had touched Atlas, something had pushed it. In celestial mechanics, there's a term for this: non-gravitational acceleration, a force acting on a body that isn't gravity, an internal push, a jet, a venting of material. For ordinary comets, this is normal. As sunlight warms them, gas shoots out through cracks in the surface, acting like tiny rocket engines. The reaction force nudges the comet slightly off course. We've seen it thousands of times. But with Atlas, the math didn't just indicate a push, it indicated a massive one. When JPL ran the momentum calculations, the numbers lined up in a way that made even seasoned analysts blink. To move Atlas by the amount measured, the object would have needed to eject roughly 4 billion tons of material. A violent, explosive mass loss event. And yet, as Segment 1 and Segment 2 made painfully clear, there was no debris, no expanding dust cloud, no streak of gas, no glowing tail torn open by the sun, nothing that could account for the push. It was exactly what one astronomer later described as a propulsion without exhaust, a force with no reaction, a push with no plume, a violation of the oldest rule in physics. For every action, there must be an equal and opposite reaction. But Atlas seemed to have taken an opposite approach, an action without a visible reaction. And before anyone could blame faulty sensors or instrument glitches, the data from independent systems rolled in. NASA's JPL, ESA's Mars Express, China's Tianwen-1, ground-based observatories in Hawaii, Chile, Italy, Spain. Different sensors, different angles, different calibration protocols, and all of them measured the same unnatural drift. This wasn't a camera glitch. This wasn't a software bug. This wasn't an artifact of light or shadow. Atlas really had accelerated, and the cosmos had swallowed the evidence. One of the physicists reviewing the early numbers, Dr. Eleanor Gates of Mount Wilson Observatory, phrased it more bluntly than anyone else dared. Momentum cannot vanish. If Atlas accelerated, something had to push, and that something is missing. Her statement circulated quietly across internal mailing lists and Slack channels. It wasn't meant for the public, but it captured what every scientist was thinking. If the push happened, where is the signature? If 4 billion tons left the object, where are the scars? If the comet vented enough force to alter its orbit, why is the sky behind it still perfectly clean? It was the kind of paradox that keeps astronomers awake at 3 a.m. and staring at plots on their monitors, whispering the same question over and over. What is pushing this thing? Because whatever it wasn't behaving like water vapor. It wasn't behaving like dust. It wasn't behaving like any known cometary jet ever recorded. It was pushing without appearing to push. And in science, when one anomaly appears, more usually follow. The invisible acceleration of Atlas wasn't an isolated oddity. It was the opening crack in a much larger fracture. A fracture that would soon tear through our assumptions about motion, mass, and the geometry of interstellar travelers. And when astronomers checked the orbit again, another impossibility emerged. For decades, astronomers have assumed one simple truth about interstellar objects. They come from anywhere, from above the solar system, from below it, from strange inclinations or steep plunging arcs. Their paths are supposed to be chaotic, uncontrolled, unconstrained by the architecture of our planets. But 3I Atlas didn't behave like an outsider entering unfamiliar territory. It behaved like something that already knew the layout. When orbital analysts laid out Atlas's incoming trajectory, the room went quiet. The object was gliding into the solar system, almost perfectly aligned with the ecliptic plane, the thin, flattened sheet where all major planets orbit the Sun. Earth, Mars, Jupiter, even the asteroids and most dwarf planets. Their paths all lie within this shared disk. But interstellar objects, they shouldn't care about it at all. Yet Atlas slipped into that cosmic highway with a tilt of only 5 degrees, a deviation so small it fell within the margin of planetary formation itself. A 5-degree mismatch in 3-dimensional space is nothing. It's the equivalent of threading a needle from miles away. The odds of a random interstellar visitor entering that plane by chance? About 0.2%, roughly 1 in 500. Rare, but not impossible. But then came the part that made astrophysicists lose their composure. Atlas wasn't just aligned with the planetary plane. It was moving in the opposite direction. Imagine a 6-lane highway where every car travels east, and suddenly, a single vehicle enters the same road, in the same lane, but driving west. That was Atlas, using the same plane as every planet, while traveling against the flow. This was not a small detail. This was not a poetic metaphor. It was a mathematical contradiction. Interstellar trajectories should slice through the solar system like random arrows, steep, crooked, diagonal, vertical, chaotic. But Atlas behaved as if it were choosing the road most crowded with observational eyes. Dr. Jerome Singh, an orbital dynamics expert, summarized the unease with one line that spread quickly across private academic group chats. Interstellar objects do not choose lanes. Atlas did. Because to travel retrograde, moving backward relative to the planetary traffic, yet stay locked within the same thin disk, suggests an astonishing level of precision. If gravitational slingshots flung it from another star system, the angle should be random, messy, even violent. But Atlas didn't enter violently. It entered smoothly, elegantly, almost deliberately, like a swimmer sliding into the current but heading upstream. For many astronomers, the question became impossible to ignore. Why this plane? Why this alignment? Why this direction? If Atlas had approached from above or below the solar system, no one would have blinked. If it had come in at a sharp incline, everyone would have shrugged. But aligning almost perfectly with the ecliptic while moving retrograde was like hearing a familiar melody played backward. It hinted at intention, or at least optimization. And the unease deepened when scientists realized something else. The ecliptic plane isn't just a geometric curiosity. It's the solar system's observational backbone, the region where nearly all spacecraft, telescopes, and monitoring instruments focus. To enter that plane so precisely feels less like coincidence and more like choreography. Even the most conservative astronomers admitted privately that the geometry didn't feel random. Patterns rarely do. And this was only the beginning. The alignment was strange. The retrograde motion was stranger. But the real shock was still ahead. A violation of a rule so fundamental that many scientists initially refused to believe the data at all. Because Atlas didn't just choose the planetary plane, it chose to defy the physics that governs every comet we've ever observed. And then came the violation no one thought possible. If the strange orbit of 3I Atlas unsettled astronomers, the next discovery outright shocked them. Because across 3 continents, at nearly the same moment, telescopes caught something they were never supposed to see. In Chile, the Atacama observatories detected it first. Minutes later, a team in Japan confirmed it. And by nightfall in Italy, yet another observatory quietly uploaded the same impossible measurement. A jet of material, a stream of particles erupting from the comet's surface, was pointing directly toward the sun, not away from it, toward it. In cometary physics, that is a forbidden act, the kind of behavior that simply does not occur in nature. To understand why this discovery rattled the scientific world, you only need to know one rule. The most basic rule. The rule every undergraduate learns by week 3 of their astronomy course. A comet's tail always points away from the sun. It doesn't matter which direction the comet is moving. It doesn't matter what angle we observe from. The tail is shaped by solar radiation pressure and the solar wind. A constant stream of charged particles blasting outward at hundreds of kilometers per second. Those particles sweep dust and gas away from the sun, creating the iconic tail that has guided human observers for thousands of years. It is so reliable, so absolute, that astronomers use the tail to determine a comet's orientation even when they can't see the nucleus. So when Atlas produced a jet that was not being pushed backward, but instead pushed forward, straight into the solar wind, the reaction among scientists was disbelief. At first, some thought it must be a trick of perspective. Sometimes when Earth passes through a comet's orbital plane, a normal tail can appear to point the wrong way. An illusion known as an anti-tail. It has fooled astronomers before. But this time, there was no mistake. Multiple observatories positioned thousands of kilometers apart recorded the same geometry. Different longitudes, different latitudes, different atmospheric conditions, all showing the same thing. The jet from 3I Atlas was pushing into the face of the sun, and it wasn't brief. The jet held steady for nearly 48 hours. That alone defied every model. Solar radiation should have bent the stream backward within seconds, just as wind bends smoke rising from a chimney. No force in the known natural behavior of comets is strong enough to maintain a sun-facing jet. But Atlas did. The data didn't show a plume being battered and twisted by the solar wind. They showed a straight, stable, unwavering line of emission, as if the jet had a mind of its own. Some astronomers whispered what others were afraid to say. This didn't look like vapor venting. It looked like thrust. Dr. Yamamoto Akira, a veteran comet physicist from Tokyo, put it into a single sentence that captured the absurdity. A sunward jet is equivalent to a stone floating upward. It simply cannot happen. Because even if Atlas had some bizarre internal cavity or random geometry that forced material out in an unusual direction, the sun's radiation should have corrected it instantly. But the jet resisted solar pressure. It resisted the wind. It resisted the rules, like a torch flame burning in a hurricane, but pointing into the wind instead of away from it. As the hours turned into 2 days, mission teams around the world waited for the jet to collapse, to bend, to yield. But it didn't. It remained straight, persistent, controlled, if such a word could even be used. And in that quiet, steady defiance, the mystery of Atlas deepened, because an object that can accelerate without a tail and vent material into the sun without bending is not behaving like a comet. It is behaving like something that understands its own dynamics. And the sunward jet, shocking as it was only one piece of a broader pattern. A pattern in which Atlas repeatedly broke the very rules that define cometary behavior. But that wasn't the only contradiction in Atlas's movement. Up to this point, 3I Atlas had already broken several of the quiet rules astronomers rely on: motion, geometry, directionality. But the next anomaly wasn't about how Atlas moved. It was about what Atlas was: its size, its mass, its speed. Individually, each number was surprising. Together, they formed something close to a statistical impossibility. When the first-dimensional models came in, the numbers felt almost unreal. A nucleus roughly 5.6 kilometers wide. A solid core the size of Manhattan, drifting between the stars. For comparison, the second known interstellar visitor, 2I Borisov, had a nucleus only a few hundred meters across. Atlas, on the other hand, outweighed Borisov by a factor of nearly 1,000. Not 10, not 100, 1,000. Astronomers stared at the data, ran the error bars, recalibrated instruments, but the results held. Atlas wasn't just a big interstellar fragment, it was huge, far larger than anything we expected the galaxy to fling our way. But the true shock wasn't its mass. It was the fact that this enormous mountain-sized object was traveling at 58 kilometers per second, 129,000 miles per hour, faster than any large comet ever recorded. To put it plainly, small objects can be flung into interstellar space at high speed. Large objects stay home. That's how astrophysics works. Ejection events, planetary collisions, stellar interactions, gravitational chaos tend to accelerate lighter debris. Heavy bodies, especially those kilometers across, are much harder to sling out of a star system. They're massive, stable, gravitationally tied. They require a staggering amount of energy to accelerate. And yet, Atlas was both. Too massive to be moving this fast. Too fast to be something this massive. Dr. Caleb Shaw, a dynamicist at Caltech, captured the contradiction perfectly. Atlas is too big to be that fast, and too fast to be that big. It was another violation of cosmic intuition, another rule bent until it cracked. When researchers tried to explain how Atlas achieved this impossible pairing of mass and velocity, only two extreme scenarios emerged. Possibility 1. A catastrophic gravitational event, something unimaginably powerful, like a near pass by a neutron star or a grazing encounter with a black hole, could, in theory, hurl a large object outward at high speed. But even that explanation struggled. Such events are extraordinarily rare, and they almost always tear objects apart, fragmenting them into smaller pieces. Atlas, however, arrived intact. A 5.6-kilometer body would not leave the vicinity of a compact star without being shredded into rubble. And yet, Atlas showed no signs of catastrophic fragmentation. Possibility 2. A deliberate acceleration mechanism, a system, natural or artificial, that imparted energy in a controlled, sustained way. Not a slingshot, but a drive. Not an accident, but an act. Most scientists avoided this path. It felt premature, speculative, but the physics kept pointing back to the same uncomfortable truth. Atlas behaved less like a random shard of rock and more like a projectile. And then came the detail that made the anomaly even sharper. As Atlas fell into the sun's gravity well, it should have slowed slightly when climbing back out. That's how hyperbolic orbits behave. But Atlas didn't noticeably lose speed. Its inbound velocity seemed almost preserved, as if whatever sent it on its way had given it more than enough energy to ignore the sun's influence. The more scientists studied its motion, the more Atlas resembled a precision-launched object, not a drifting refugee of interstellar chaos. An improbable traveler, a statistical bullet, an object that simply should not exist in this combination of size, weight, and velocity. One anomaly is interesting. 2 anomalies are concerning. 3 or 4 begin to form a pattern. And Atlas, by this stage in its journey, had broken every pattern we thought we understood. Its acceleration made no sense. Its jet pointed the wrong way. Its entry angle defied randomness. Its mass-velocity pairing defied probability. And there was more to come. Much more. And yet, its path through our solar system looked almost choreographed. From the moment 3I Atlas crossed into the inner solar system, its behavior stopped looking random. It began to look aware. Not conscious, no one was claiming that, but coordinated, timed, almost strategic. If its mass and velocity made it a statistical bullet, then its trajectory made it a guided one. Because when astronomers reconstructed its flight path in detail, something eerie emerged. Atlas passed by nearly every major orbital observation post in the solar system, at the exact moments those spacecraft were active. 1. The Mars flyby. A perfect window. Atlas swept past Mars in September 2025, coming within tens of millions of kilometers. Just close enough for high-resolution imaging. And what was Mars doing at that time? Both ESA's Mars Express and the Trace Gas Orbiter were online, running full operations. No safe mode, no blackout periods, no solar conjunction interruption. Had Atlas arrived a month earlier, Mars Express would have been offline for calibration. A month later, TGO was scheduled for software updates. But Atlas threaded the needle. It passed during the one clean observation window. Its trajectory looked less like a cosmic accident and more like a scheduled appearance. 2. The Venus encounter. Another coincidence. 2 sharp weeks later, Atlas curved inward and drifted near the orbit of Venus. And once again, without missing a beat, ESA's and JAXA's Venus orbiters were fully active. Akatsuki, Solar Orbiter, Bepi Colombo, they all had visibility. Their instruments were pointed outward, available, hungry for data. Had Atlas chosen nearly any other time in its 12,000-year orbital cycle, Venus's spacecraft would have been blind, behind the sun, or mid-hibernation. But no, the timing was flawless. As though Atlas knew exactly when the robotic eyes around Venus would be awake. 3. The Jupiter skim. Close, but not too close. As Atlas continued outward, its path brushed the gravitational outskirts of Jupiter, not enough to disrupt its trajectory, not enough to be captured, but close enough for long-range imaging by instruments orbiting the giant planet. This is the region where a slight deviation could have thrown Atlas off course, or even torn it apart. But the object skimmed the zone perfectly. Not by luck, not by chance, with finesse. The kind of precision that made orbital analysts stare at their simulation maps in cold silence. 4. The disappearing act, perihelion behind the sun. And then came the moment that pushed the anomaly into the realm of the uncanny. When Atlas reached perihelion, its closest approach to the sun, the moment when it should have been brightest, when Earth's telescopes should have captured the most dramatic images. Atlas passed directly behind the sun from Earth's line of sight, not partially behind, not near the solar disk, dead center in the glare. It was the single worst possible angle for every ground-based telescope on Earth, and even most space telescopes. Atlas became invisible at the very instant it should have revealed the most, like an actor stepping behind the curtain at the crescendo. Astronomers ran the probability for an interstellar object to pass directly behind the sun from Earth's perspective, precisely during its brightest phase, roughly 1 in 20,000, not impossible, but close. And when paired with the Mars timing and the Venus timing and the Jupiter skim, the coincidence began to feel like choreography. The implications no one wanted to say out loud. Atlas flew past Mars when Mars had watchers. Atlas flew past Venus when Venus had watchers. Atlas approached Jupiter when Jupiter had watchers. Atlas hid behind the sun when Earth was watching. And as Dr. Susan Marlowe of Johns Hopkins APL put it, Atlas flew past every major orbital century at exactly the right time. It wasn't just visible. It was visible at the best possible angles to our machines, but carefully invisible to the naked eye of Earth. Too perfect, too clean, too synchronized with human observation patterns. This wasn't the behavior of a random traveler drifting through our neighborhood. This was the flight path of something that slipped through our system with eerie efficiency. Optimized not for gravity, but for being seen by machines, not by people. And the closer scientists looked, the more they realized that Atlas wasn't just violating physics, it was violating probability. Because even coincidences have limits. There was a growing sense, quiet, private, unspoken, that someone or something had designed this flight path with more purpose than nature normally allows. A trajectory that made the solar system feel less like empty space and more like a survey route. But this wasn't the deepest mystery, because if the behavior looked engineered, the material looked even stranger. But what Atlas was made of raised even deeper questions. If the flight path of 3I Atlas raised eyebrows, its composition raised an entire field of science. Because when the first spectral readings came in, data collected from Chile, Italy, Japan, and confirmed by Mars orbiters, astronomers expected the familiar chemical profile of a comet, a dominance of water vapor, a mix of silicates, a healthy spike of iron, trace volatiles like carbon monoxide and cyanides. Instead, the spectral lines glowed with something far stranger: nickel, stronger, sharper, and more abundant than iron. For anyone in astronomy, that detail alone was jaw-dropping. In every known comet, every dusty traveler from the Oort cloud, every icy relic from the outer system, iron is always dominant. Iron defines their crusts. Iron shapes their spectra. Iron tells the story of their birth. But Atlas broke that narrative entirely. Here, nickel outshined iron by a margin no natural model predicted. It wasn't just a tilt in chemistry. It was a reversal, an inversion of the cosmic recipe. And it got stranger. Mixed within the nickel-rich signature were intense concentrations of nickel cyanides, compounds that form under extreme heat and pressure, conditions rarely found in typical cometary environments. These were not faint, ambiguous lines. They were bold, unmistakable, louder than anything seen in the catalogues of comet spectra. For a moment, teams wondered if the data was contaminated, instrument error, sensor ghosting, interference. But both ESA and JAXA repeated the readings independently. The ratios held firm. Nickel-iron, nickel cyanides at levels off the charts, a profile that simply did not match anything born in a cold, icy region of a young star system. This led several researchers to a provocative comparison. If you were to engineer a material to withstand extreme temperatures, stress, and thermal decay, to survive the brutal vacuum of interstellar space for millions of years, you might choose a nickel-based alloy, just as aerospace engineers on Earth have done. Nickel superalloys power our jet engines. They line spacecraft heat shields. They endure radiation, pressure, and temperature swings that would fracture steel. And here, drifting through the solar system, was an interstellar object whose chemistry resembled, uncannily, those same industrial-grade materials. Was Atlas an engineered structure, a heat-hardened relic, a shard of something ancient and purpose-built? The conservative explanation is that Atlas originated in a star system very different from ours, one where intense heat stripped away lighter elements early, leaving a dense metallic core. This could, in theory, tilt the chemistry toward nickel, but even that scenario struggled. Natural processes don't create such pure, such selective, such unbalanced elemental profiles, not without leaving traces of magnesium, silicon, or other metals. Atlas seemed too clean, too deliberate. Dr. Pavel Ignatiev, a spectral chemist at the European Southern Observatory, offered a line that spread quickly across scientific circles. This is not a comet's fingerprint. It's something else entirely. The emotional reaction within the community wasn't fear. It was fascination, a new door creaking open, revealing a material story that didn't belong to any comet we've catalogued. Because if Atlas's orbit hinted at optimization, and its motion hinted at control, its composition hinted at endurance, perhaps the object wasn't fragile ice at all. Perhaps it was something built to survive, something old, something hardened, something forged in a furnace beyond our own. And if the chemistry was bizarre, what came next was even stranger. And the odd chemistry didn't end there. If 3I Atlas's nickel-rich chemistry was strange, what came next pushed astronomers past confusion, into disbelief. Because when the volatile analysis results were finalized, after weeks of cross-checking between ESA, JAXA, and ground-based observatories, the numbers told a story no comet should ever tell. Ordinary comets, the kind that orbit our sun, are essentially dirty snowballs. They're made of 70 to 80% water ice, mixed with dust and trapped gases. That water is what drives their behavior. When a comet heats up near the sun, the ice sublimates, turning solid into vapor and exploding outward as jets that form tails, fans, and plumes. Without water, a comet cannot breathe. It cannot produce the jets that push it off course. It cannot brighten dramatically. It cannot shed mass in any meaningful way. Water is the engine, the heart, the fuel. But Atlas had almost none, only 4%. Not 70, not 50, not even 20, just 4. A number so low it pushed the object out of the category of comet entirely. To a physicist, that was equivalent to examining a shark and discovering it has no skeleton. The structure shouldn't work. The behavior shouldn't exist. And yet Atlas was one of the most active interstellar objects ever observed. A jet firing toward the sun, a 48-hour plume that defied radiation pressure, a 4 billion-ton mass loss event, a brightening surge that lasted 70 days. None of these phenomena should be possible without water, not even close. The paradox deepened. How does a nearly waterless object produce more dramatic activity than comets overflowing with ice? Astronomers proposed a few possibilities. Perhaps other volatiles, like carbon monoxide or carbon dioxide, were taking water's place, but the spectral lines didn't support that. Perhaps nickel vapor or silicate gases were erupting from deep fractures, but those would require temperatures far beyond what Atlas should experience. Perhaps the jet wasn't a natural vent at all, but something more regulated. And then came the most unsettling detail of all. Despite losing an estimated 4 billion tons of material, Atlas showed no signs of breaking apart, no fragmentation, no structural collapse, no violent shattering. It remained whole, stable, intact. A typical comet that lost even 1% of its mass this quickly would begin to fracture like a brittle stone, splitting into pieces under its own stress. But Atlas behaved like something built for endurance. A rigid, hardened body forged to survive extreme heat and extreme loss. Dr. Helen Grossman, a planetary geologist at the University of Arizona, summarized the shock in a single sentence. Atlas behaves less like ice and more like armor. Armor. The word hung in the academic air like a taboo, but it captured exactly what scientists were seeing. A body with too little water to be a comet, but too much resilience to be a rock. A traveler that shed mass like a comet, but stayed intact like metal. And if the interior chemistry was bizarre, the next anomaly pushed the mystery onto its surface, to the way Atlas interacted with light itself, and then astronomers looked at the surface itself. By now, 3i Atlas had broken rules about motion, mass, chemistry, and water content. But the next anomaly touched something deeper, something almost philosophical: how the object handled light. To understand why this shocked astronomers, we need a quick, simple idea. When light reflects off a rough surface, dust, ice, rock, the waves scatter in different directions. But some of those waves align, creating polarization. Most comets produce a familiar, predictable polarization pattern. It's so consistent that astronomers use it to estimate dust size, texture, and even porosity. But Atlas didn't just deviate from that pattern, it inverted it. Extreme negative polarization. A first in history. Measurements from Japan, Italy, Chile, and Mars orbiters all showed the same astonishing result. Atlas was generating extreme negative polarization. Instead of reflecting light in a way that aligned certain components, Atlas seemed to twist the light, bending the polarization backward, almost like a mirror that doesn't just reflect, but filters. No known cometary surface, no dust cloud, no mixture of ices, no known mineral frost can produce this effect at the magnitudes observed. Negative polarization this extreme is almost never seen in nature, and when it is observed, it usually comes from ultra-fine engineered films, polished microstructures, laboratory optical coatings, materials intentionally shaped at microscopic scales. In other words, things built, not things formed. Atlas wasn't behaving like a dusty snowball. Its light signature looked more like a surface, smooth, dense, fine-grained, beyond natural expectation. A surface too refined to be a cometary crust. Scientists began comparing Atlas's optical behavior with exotic materials used in aerospace and photonics research, the kind engineered to handle extreme radiation or control thermal emission. The match was unsettlingly close, as if the object was processing light. For decades, comets have obeyed a basic optical grammar. They reflect light based on dust particles, irregular, chaotic, unstructured. But Atlas seemed to be doing something else entirely. Not just reflecting, but manipulating. Dr. Koji Tanaka, an expert in light scattering at Kyoto University, put it into a sentence that spread like wildfire in scientific circles. Atlas doesn't reflect light, it manipulates it. The phrase wasn't meant as poetry. It was a literal interpretation of the data. This wasn't a comet hiding behind dust. It was an object handling photons in a way that suggested microstructure, patterns smaller than wavelengths of visible light, tiny ridges, metallic grains fused into a near-continuous film, a plasma-hardened crust. No one could say for certain, but one truth became impossible to avoid. The surface of Atlas looked engineered, either by physics we don't yet understand, or by processes we've never seen in natural objects. The idea whispered through the research labs wasn't aliens. It was simpler. Atlas looks old, hardened, designed to endure. This tied disturbingly well with earlier anomalies. The lack of water, the nickel-rich shell, the structural resilience after losing billions of tons. Piece by piece, Atlas was drifting out of the category of comet and into something else, something that raised an older question, not about what Atlas is, but where it came from. Because when astronomers traced its path backward through the stars, the geometric coincidences became almost mythic. But the biggest chill came from its origin path. For many astronomers, the anomalies of 3I Atlas were already overwhelming. But when its inbound trajectory was traced backward into interstellar space, the mystery took a turn that felt almost mythic, because the object appeared to come from a region of the sky that carries one of the most haunting echoes in the history of SETI. A brief return to 1977, the night of WOW. On the night of August 15, 1977, the Big Ear Radio Observatory in Ohio recorded a narrowband radio burst, strong, clean, and unmistakably structured. It lasted 72 seconds, then vanished forever. The burst was so anomalous, so utterly unlike background noise, that the astronomer on duty, Dr. Jerry Amon, circled the printed data with a red pen and wrote a single word in the margin. Wow. For nearly half a century, no one has explained it. The signal never repeated. No spacecraft, pulsar, or natural phenomenon has ever produced anything quite like it. And its origin point? A quiet stretch of sky near the constellation Sagittarius, close to the star group Chi Sagittari, a place no one expected anything unusual to happen again. Until Atlas. Atlas emerges from the same celestial corridor. When orbital analysts traced Atlas's trajectory back into interstellar space, they found something chilling. The path intersected the same general corridor of sky that produced the WOW signal, within roughly 9 degrees. Not an exact match, but close enough to make radio astronomers freeze in place. Statistically, the odds of a random interstellar object entering the solar system from within that narrow band of sky are less than 1%. Not impossible, but rare enough to sit uncomfortably between coincidence and pattern. No one claimed a connection. No one dared. But the symmetry was unmistakable. 2 unrelated anomalies, 48 years apart. One a mysterious radio burst, the other a comet-like object that broke nearly every physical rule, originating from nearly the same region of the galaxy. The coincidence was so striking that SETI reactivated surveillance dishes and scanned the corridor again during Atlas's approach. They heard nothing. No whisper, no pulse, no echo of 1977. If the WOW signal had been a message, it was now long silent. If Atlas had been a visitor, it did not announce itself. The cosmos offered only geometry and silence. The emotional impact of this alignment was subtle but profound. Astronomers who had spent their careers avoiding sensationalism now found themselves staring at two anomalies separated by almost half a century, connected only by direction. A coincidence? Almost certainly. But still, the question lingered in the quiet halls of observatories. Why did two of the strangest events we've ever recorded come from the same patch of sky? Dr. Jerry Amon himself once said, "We may never know what WOW was, but we'll always wonder why it came from there." And now, Atlas had come from there too, or close enough for the symmetry to feel deliberate. But as eerie as the WOW signal alignment was, it wasn't the anomaly that broke cometary physics. The final anomaly, the 10th one, the one that stunned both NASA and CNSA, returned us to the heart of the mystery. How does a comet lose 4 billion tons and leave no tail? And finally, anomaly number 10, the one that shattered comet physics. The night of October 29th arrived without fanfare. No meteor shower, no solar flare, nothing unusual in the sky. And yet, somewhere between Mars and the Sun, 3I Atlas did something no comet in recorded history had ever done. It turned on. A five-fold surge instantly across observatories in Chile, Hawaii, Italy, and aboard orbiting spacecraft. The brightness readings all spiked upward, clean, sharp, and immediate. Not gradually, like normal comet outgassing, not chaotically, like dust storms or fragmentation, but in a single, flawless step function, a five-fold increase in luminosity, instantly. Astronomers stared at the real-time graphs, unable to speak. This wasn't a flare, it was a switch. And the color? That made the mystery even deeper. A blue glow like ionized plasma. Ordinary comets glow yellow-white, the warm, dusty signature of vaporized water and scattering ice particles. But Atlas flared blue, cold, sharp, electric. Spectral analysis revealed no increase in dust, no surge in water vapor, and no significant mass loss. Yet the luminosity persisted, steady as a lighthouse beam in deep space. A glow that held for 70 days. Most comet brightening events last hours, sometimes days, rarely weeks. Atlas's blue emission held for 70 straight days. No flicker, no decline, no dust tail, no fragmentation, no physical mechanism anyone recognized. It behaved less like vapor and more like a sustained excitation, as if something was being energized, charged, or activated. Some astronomers suggested electromagnetic interactions, perhaps solar wind exciting a conductive surface. Others murmured about exotic crystal lattice reactions, a kind of cosmic piezoelectric effect on a metallic crust. None of these explanations were comfortable. All were theoretical edge cases at best, but the data was undeniable. Brightness up 5 escale, color shift to deep blue, 0 dust increase, 0 added mass loss, 70 days of stability. It was the most sustained, dust-free brightening event ever recorded. And throughout it all, Atlas remained eerily smooth. Its coma, spherical, symmetrical, as if the glow were emanating from within, not scattered from without. A signal, not a shine. Dr. Ana Velasquez put it bluntly. Atlas didn't shine, it signaled. To her, this wasn't the behavior of a crumbling ice body. It resembled an emission event, a controlled release of energy, not a natural flare. Not everyone agreed, but no one could deny the strangeness. Because the moment the glow finally softened, quiet, gentle, almost fading into the background of sunlight, Atlas returned to its previous brightness as if nothing had happened. No debris, no new jets, no mass loss, just silence. The calm, before the revelation. For 2 months, astronomers debated the meaning of the blue glow. Was it a structural stress release, a solar interaction resonance, or something beyond our models entirely? Whatever the cause, the event set the stage for the most stunning anomaly of all, one that didn't just bend physics, It shattered it, because when the light faded and Atlas moved past perihelion, the truth became impossible to ignore. It had lost 4 billion tons of mass and left absolutely nothing behind. But when the light faded, the real mystery stood naked. For weeks, the blue glow had fascinated astronomers. But when it finally faded, when Atlas returned to its quiet, dim state, the universe revealed something far stranger. Something that shouldn't just be impossible. It should be visible. Because only then did researchers realize the true magnitude of what Atlas had done. The hard numbers don't lie. NASA's Jet Propulsion Laboratory, ESA's orbital probes, and China's Tianwen-1 had all agreed on one thing. Atlas experienced strong non-gravitational acceleration, meaning it pushed itself. And the only way a comet-sized body can accelerate without engines is by throwing mass backward, expelling gas, dust, vapor, or debris at immense speed. Through the equations of momentum conservation, engineers calculated the amount of mass Atlas must have lost, about 4 billion tons, a chunk of itself the size of a mountain. Nothing in astronomy is vague about this. Momentum is momentum. Acceleration cannot appear out of nowhere. But when astronomers turned their instruments toward the space behind Atlas, there was nothing. The sky behind Atlas was empty. Spain saw nothing. Italy saw nothing. Hawaii saw nothing. Mars orbit saw nothing. Even long exposure, deep field composite imaging showed only blackness. No tail, no plume, no ejector, no particulate stream fading into the void. The region of sky where 4 billion tons of dust and gas should have been blazing like a cometary scream was silent. Not dim, not faint, not dispersed, empty. It violated the most basic law of comet physics, a rule so reliable that astronomers use it to identify comets even without seeing the nucleus. The 10th law of Comet. Broken open. The law is simple. If a comet loses mass, it must show its scars. A comet's tail is not optional. It's the direct consequence of material being ripped from the surface. It's the signature of destruction. And yet Atlas had torn 13% of its body into space. Theoretically, enough dust to paint a streak millions of kilometers long, and left no scar. This wasn't subtle. This wasn't ambiguous. This was the cosmic equivalent of an explosion happening without smoke, sound, or debris. As one researcher described it, a ship crossing an ocean, leaving the water still. Atlas had accelerated but hid the consequence. It had shed mass but erased the evidence. And in doing so, it broke the very idea of what a comet is. A comet that keeps its secrets. Dr. Matteo Rossi of the University of Bologna summed it up perfectly. A comet without a tail is not a comet. It's something wearing a comet's mask. The phrase echoed across observatories. This wasn't poetic exaggeration. It was a diagnosis. Because the more astronomers searched for the missing tail, rechecking instruments, recalibrating sensors, rerunning low-light contrast filters, the more obvious the conclusion became. Atlas wasn't just abnormal. It was deliberate in its silence. No known mechanism can produce acceleration without visible ejector. No known chemistry can evaporate billions of tons without leaving spectral signatures. And no known comet can survive such mass loss without fragmenting into rubble. Yet Atlas survived, accelerated, brightened, and concealed the one thing no comet has ever been able to hide: its wake, the breaking point. This was the anomaly that broke the others open. This was the moment the scientific community accepted that something truly unprecedented was unfolding. The missing tail wasn't just another irregularity. It was the keystone anomaly, the violation that proved Atlas wasn't following the rules of any known process, natural or otherwise. And the question that followed was inevitable. How do you explain an object that defies every explanation? So scientists turned to probability, and probability broke. For weeks, astronomers tried to hold onto the idea that Atlas was merely unusual, an outlier, a rare comet, a statistical curiosity. But as the data accumulated, that comfort collapsed. Because by late 2025, the scientific community wasn't dealing with one anomaly. It was dealing with 10, each one improbable on its own, each one documented across independent instruments, each one refusing to fit into any model ever written. The 10 anomalies. Side by side. When the major observatories finally pooled their datasets, the full picture looked like this. Non-gravitational acceleration with no ejector. Perfectly planar orbit aligned within Schokkansphäre, retrograde motion along that plane. Sunward Jet lasting 48 hours. Optimal flybys of Mars, Venus, and Jupiter, then vanishing behind the Sun. Size and speed paradox. Too massive to move that fast naturally. Nickel-rich chemistry, stronger than iron. Water content only 4%, yet powerful sustained outgassing. Extreme negative polarization, surface manipulating light. 4 billion tons missing, and still no tail. 10 independent irregularities. 10 documented violations of comet physics. A single abnormal trait can be explained away. 2 can be rationalized. But 10, and that's when statisticians stepped in. The multiplied probability researchers at 3 separate institutions, the Harvard-Smithsonian Center for Astrophysics, the European Southern Observatory, and the Italian National Institute for Astrophysics, each ran independent probability models. The results converged. The chance of all 10 anomalies occurring together by accident was less than 1 in 100,000. Some models put it closer to 1 in a million. This wasn't speculation. This wasn't fringe analysis. These were mainstream astrophysicists using the same statistical tools employed in exoplanet detection, solar dynamics, and cosmology. Atlas wasn't just rare. By current models, it was nearly impossible. Simulation versus reality. Harvard runs the numbers. To verify the math, the Harvard-Smithsonian team generated Monte Carlo simulations across 2,000 known cometary orbits, testing for combinations of trajectory angle, velocity profiles, sublimation patterns, material composition, jet geometry, tail formation. The outcome: 0 simulations produced anything resembling Atlas. The models failed not because of computational errors, but because no natural scenario could recreate the observed pattern. ESA and JPL double-checked the sensors. Skeptics suggested that perhaps the discrepancies were observational. Sensor biases, calibration errors, or misinterpretation of faint signals. So ESA and NASA's Jet Propulsion Laboratory conducted full cross-calibration tests on trajectory vectors, brightness curves, spectrographic signatures, polarization angles. Nothing broke. The vectors remained consistent. The mass loss calculations held. The absence of ejecta was confirmed. Not only were the anomalies real, they were robust. Then Avi Loeb entered the conversation. Harvard astrophysicist Avi Loeb didn't claim Atlas was artificial. He didn't invoke aliens, probes, or intentions. What he said was far more measured and far more unsettling. When anomalies cluster, you widen the hypothesis field. In other words, when you run out of natural explanations, you don't jump to conclusions, but you also don't shut the door on possibilities. That sentence rippled through departments worldwide, not because it was bold, but because it was cautious. A closed-door meeting at Max Planck. In late November 2025, the Max Planck Institute for Astronomy held a private workshop with experts in orbital dynamics, plasma physics, spectroscopy, and SETI, The confidential summary eventually leaked into academic circles. Proceed without presumption of naturality or artificiality. Not natural, not artificial, just unknown. It was the first time a major scientific institution formally acknowledged that Atlas couldn't be comfortably classified by any existing framework. NASA, shocked, but careful NASA, avoided sensational headlines. It didn't declare Atlas artificial. It didn't dismiss the anomalies. What it did say was that the object presented non-trivial challenges to current Comet models. Privately, according to several researchers, NASA was stunned by the missing tail paradox and the nickel-dominant chemistry, both nearly impossible to reconcile with standard formation theories. Publicly cautious, privately alarmed. The debate tightens. By the December, two camps had emerged. The traditionalists argued Atlas was an extreme natural outlier, a statistical miracle born from a universe of endless variety. The expansionists argued that dismissing the artificiality hypothesis was no longer scientific, but ideological. And in the middle stood the data, cold, consistent, and impossible to interpret without breaking something. Dr. Hannah Brunner phrased it perfectly. Atlas forces us to confront the limits of our own models. The debate wasn't about aliens. It wasn't about science fiction. It was about humility. Because Atlas had shown, with ruthless elegance, that our understanding of cometary physics was not complete, and perhaps never was. And now the question remained. If Atlas wasn't behaving like a natural object, then what was it? So what was Atlas? A monster of nature, or something else entirely? In the final weeks of 2025, as Atlas slipped farther and farther from the Sun, the arguments on Earth grew quieter. The simulations slowed, the debate softened, and what remained was something far older than science. A sense of wonder. Because no matter which explanation one favored, Atlas had done what few cosmic visitors ever manage. It changed the way we look up. The natural extreme hypothesis. For many astrophysicists, the most conservative explanation is also the most comforting. That Atlas is simply the product of a universe more varied than our textbooks ever accounted for. In this view, Atlas is a natural extremity, not an artifact. Its bizarre nickel-rich composition, perhaps it was forged near a hot, ancient star, where iron evaporated early and heavier metals condensed in unusual proportions. Its near-total lack of water. Maybe it endured millions of years of erosion as it wandered through dense interstellar radiation fields, stripping away volatiles until only a metallic skeleton remained. Its strange acceleration, its symmetric glow, its sunward jet. All extreme behaviors, yes, but perhaps still natural in a cosmos full of strange laboratories we have yet to witness. In this hypothesis, Atlas is the universe reminding us that our sample size, just 3 known interstellar visitors, is far too small to define normal, a statistical outlier, but not a miracle. The artifact hypothesis. And yet, a quieter, more provocative interpretation lingers. Atlas behaved like something built for endurance, a body hardened beyond any known comet, a surface capable of manipulating light, a structure that lost billions of tons without fragmenting. It flew a trajectory that passed every active orbital probe and avoided Earth's line of sight at its brightest moment. Almost like reconnaissance, its nickel-rich signature resembled heat-resistant alloys we ourselves use in spacecraft. And the silent 70-day blue emission appeared more like activation than sublimation. None of this proves design, but none of it fits comfortably within natural models either. To those open to the possibility, Atlas might be more than a rock. It could be an artifact, a relic of something ancient, a probe no longer active, a hull drifting between stars long after its creators vanished. Not a messenger, not a threat, just a survivor. And yet, silence. For all the speculation, one thing defines Atlas more than its anomalies: its silence. No transmission, no encoded pulses, no change in rotation rate, no behavior resembling intelligence. Atlas never said a word. It simply passed through, calm, steady, and indifferent, like a traveler with no need for conversation. And then, without ceremony, it left the inner solar system and began its long return to the dark between stars. A silent wanderer, carrying secrets that may not be meant for us to decode. What else is out there? Atlas leaves behind a question far larger than its own mystery. If this is the third interstellar object we've ever seen, and it is already this strange, what will the 10th look like? The 50th? The 100th? How many shapes? How many chemistries? How many stories cross the void between stars without ever slowing down long enough for us to greet them? Dr. Livia Santos, in a quiet panel discussion near year's end, summed up the sentiment shared by both skeptics and dreamers. The universe rarely gives answers. It gives visitors. Visitors that change us, teach us, challenge us. Not with explanations, but with questions. A final look back. Atlas came and went without warning, without message, without identity. And yet its passage left humanity different, more humble, more curious, more aware of how much we still don't grasp about the cosmic ocean around us. Maybe Atlas was natural, maybe it was not, but either way, its existence enlarges the possible. And perhaps, somewhere in the darkness beyond the sun, another traveler is already on its way toward us, silent, ancient, and waiting. And perhaps, somewhere in the dark, the next visitor is already on its way.